Okay, so in this video, we're going to review few key things from the electricity gap fill that we did in the previous lesson. So, starting off with definitions, these are things you just have to know. You can't get around these. You just need to get some repetition in, know what these are. So, current is the rate of flow of charge. Potential difference is the energy transferred from each charge by a power source. EMF is the energy transferred to each energy charged by a power source, and resistance is potential difference divided by current. You just have to know those. Okay, so this one threw up a little bit of difficulty. So the diagram on the left, most people know that this shows an analog based device, and people know that the one on the right shows a digital. So an analog device can output any value inside its range. So this one, its range goes up to 100, so it can output any number between 0 and 100. There is no restriction on that. This digital meter, we don't know what its maximum range is here, but we know there are lots of numbers it cannot output. So it can do 5.00, it can do 5.01, it can do 5.02. It can't output 5.005. There is no option for doing it. So that's why we call it a digital device, because it can only output certain values. That's what digital means. So whatever kind of ammeter we use, we know we should be connecting that in series. If we're using a voltmeter, we know that should be in parallel with the component. That was fine. Okay, so again, just definitions and descriptions that you have to know. So two components are in series if a charge goes through one of the components and it must go through the other, and vice versa. So you can get situations where every charge that goes through one goes through the other, but it doesn't work the other way around. It has to work both ways. If they're in parallel, a charge cannot go through both. It must have to pick either one or the other. Okay, so then the current and potential difference rules in circuits, again, something you just have to know. So in series, current is the same in all components, and potential difference gets shared between them. In parallel, it's the current that splits between them and the potential difference that is the same. Again, you just have to know that. So put the current in order from highest to lowest. So I'm going to show you this, and then I'm going to dig into a little bit more why, because this causes a few cool problems. So the first two, the biggest ones, are going to be A1 and A4. It doesn't matter which way around. I could equally have put A4 in here and A1 in here. It doesn't matter. The next biggest is going to be A3, and the smallest is going to be A2. So I want to dig into that a little bit more and explain that in a bit more detail. So I'm going to do it by way of analogy. So what I've got over here is essentially an analogous water circuit to kind of visualize what this looks like. So this blue is all the water in the circuit. The battery we've just replaced with a pump. That's what makes a current flow, or in this case, water molecules move around the circuit. So A1 is going to have to be equal to A4, because if, let's say, 5 water molecules per second, I know it's incredibly small, but we're just for the sake of example, let's say 5 water molecules per second go through A1, 5 would have to go through A4 because water is incompressible. You can't make water molecules move close together, so we can't move them through A1 and not through A4. We need the whole system to move at the same time. So if 5 go through here per second, 5 must go through here per second. That's why A1 and A4 are the same. In terms of A2 and A3, hopefully this visual helps you see how this works. So the way I imagine it is a big resistance is like a really narrow pipe, whereas a smaller resistance is like a wider pipe. So hopefully you can see from this diagram that we're going to be able to get more water per second through A3 than we are through A2, because A3 is much wider. So that's why A3, the current, is bigger than A2, because it's going through a smaller resistance. But if we were to add A3 and A2 together, that would equal A1 and A4. Okay, so that's that one. looking at the same thing with potential difference. So in this one, again, I'll show you and then I'll talk about why. So the biggest one is going to be V1. That's measuring the EMF of your power supply. That would be equal to the sum of V2 plus V3, which is why it has to be the biggest. The next biggest one is going to be V2, and then it's going to be V3. And again, I want to dig into that a little bit more and explain why V2 is bigger than V3. So things we know about the circuit. So we know the current passing through both resistors is the same. That's what allows the following logic to work. That you have to have the current the same to follow this logic. So the resistance tells you how much work you have to do to pass a current of 1 amp through the component. So let's say, for example, we've got a current of 1 amp in this circuit. That would mean we need a potential difference of 10 across here and only a potential difference of 5 across here. It takes twice as much work to have a current of 1 amp through here as it does through here, and that would mean that V1 would have to be 15 because we'd have to add them together. So that's what potential difference is. It's a measure of how much work it takes to move a charge through a component. So a larger resistance means more work, which means a larger potential difference. So this is something we can do with series circuits. And actually, if the resistance is double, that means you have to do twice as much work, so the potential difference will be double. So V2 is going to be double V3. So like I said, if there was a current of 1, this one will be 10, this one will be 5. So you can see that it is in fact double. Okay, so let's continue. Okay, so again, some just general rules that you have to know. So adding resistors in series acts to increase the total circuit resistance. A few people put increasing in here, which doesn't make grammatical sense. The total circuit resistance, so it increases the total circuit resistance, and and it acts to decrease the current. So bigger total circuit resistance means decreased current supplied by the power source. And it's exactly the opposite in parallel. So adding resistors in parallel opens up more pathways for your charges to go through. Oh, I accidentally right click it there. So it's going to decrease that. And if you decrease the total resistance, that increases the current supplied by your power source. So how do we actually increase the resistance of something? So the resistance of a wire can be increased by increasing its length. Again, a few people put increase in here, but that doesn't make grammatical sense. By increasing its length, increasing its temperature, or by decreasing its cross-sectional area. These three things would all make resistance bigger. So length and resistance actually have a directly proportional or proportional relationship. So doubling the length doubles resistance, whereas cross-sectional area and resistance actually have an inversely proportional relationship. So doubling the area actually halves the resistance. That's what that means. Okay, so let's dig into that a little bit more so we can actually understand how that works. So if an electron travels through a longer wire, it will have more collisions with the metal atoms. So that's kind of our source of resistance in our circuit. The electron's collisions with atoms as it moves through the wire. So longer wire, more collisions. And that means that the electron's speed decreases. So if it has more collisions, that means it can't travel as fast through that. And if you've got the electrons moving slower, that's one factor that means the current decreases. And that's why we say the resistance increases, because it decreases the current. A large cross-sectional area means that more electrons can pass through a point per second, because if it's wider, you can get more through. And that's another factor that can cause the current to increase. At a higher temperature, the electrons and atoms experience larger random motion. So imagine them like vibrating around, which means that they will have more collisions as the electron moves through, which decreases the electron's speed and so decreases the overall current. So there's a few factors that affect the current going through a component. how wide uh, that component is, and how fast electrons can move through the component. Those are our two factors, and then length and temperature change that speed. Okay, so we've had a few issues with this one. So match the current versus potential difference graph to its description. So um, the fixed resistor looks like this, sometimes known as an ohmic resistor. So this graph shows the resistance is the same everywhere because V divided by R, I, is the same everywhere on this graph. And that means we can actually do two more, because a thermistor, if you keep the temperature the same, its resistance stays the same, so it acts like a fixed resistor. And an LDR, if you keep the light intensity on it the same, its resistance stays the same, so again, acts like a fixed resistor. The only one which the resistance changes is a filament bulb, because at larger currents and potential differences, it gets hotter, which means its resistance increases. So we need this graph. This one shows that at higher potential differences in currents, the resistance has actually got bigger. So that's our filament bulb graph. Okay, finally, looking more specifically at the thermistor and LDRs, again, some rules you just have to know. A thermistor is a device where the resistance decreases as you increase its temperature, so it behaves in the opposite way to normal components, because pretty much everything, if you increase the temperature, its resistance increases. A thermistor is a special type of semiconductor where you can actually decrease the resistance. An LDR works in the same kind of way. If you increase the light intensity on it, it decreases its resistance. Because what actually happens in both of these cases is you release more free electrons in the conductor itself, and more free electrons means you get a higher current or a lower resistance. So that's what's actually going on there.